Who doesn't love a snow day? I figured while we got a little bit of snow, I'd go out in my backyard and do some skiing. Whoa. Well, this is actually pretty fun. I can't believe I can do a podcast and ski at the same time, but that's what happens when you're awesome like I am. So I'll go ahead and finish skiing and you go ahead and watch the rest of this podcast. But some of this will be review and some of it will be new, so keep up, will you? Bonds are just this. What are the forces that hold atoms together? These are the things that I want you to be able to do with a couple added things. We're going to talk about isomers, and we're also going to talk about two techniques to figure out what the bonds are, what molecules are, what shape they are, those kinds of things. So when we talk about bond energy is measured by how much energy takes to break that bond. The higher the bond energy, the stronger that bond is. So a single bond between carbons has a certain amount of bond energy. A triple bond between carbons has much more bond energy. That tells us that that triple bond is stronger. If we want to look at how do bonds form, well, way off over here, these two H's are too far apart. As they get closer and closer together, they reach an area of lowest energy, and that's where everybody wants to be. They want to reach an area of lowest energy. And so the curve starts to dip down. And then at the bottom of the curve, that is the primo spot. That's where you want to be. That's where it's just right. It's not too far apart. It's not too close together. When you get too close together, the nuclei start hating on each other and push each other apart. So you want to find that magical spot right there in the middle, and that's what determines bond length. And for every molecule, it's going to be a little bit different. For carbon-hydrogen, it's going to be different for a hydrogen-hydrogen. But you want to find that distance that gives you the lowest overall energy. You need to know the definition of electronegativity, but I think you already knew that. And electronegativity has to do with polarity of a molecule. So we've already talked about intermolecular forces, and intermolecular forces are due to dipoles, right? So sometimes they're instantaneous, and sometimes they're sustained. We're going to say that every bond that we form is trying to get what we call Ndeck. Ndeck. You heard me, Ndeck. And what is Ndeck? Noble gas electron configuration. For two nonmetals, they're going to share electrons. For a metal and a nonmetal, otherwise ionic stuff, metals are going to lose electrons and get Ndeck, and nonmetals are going to gain electrons and achieve Ndeck. And what that means is they're going to take on the electron configuration of some noble gas. So sodium has 11 electrons. It will lose one and have 10 electrons, just like neon does. For bond energies, we can figure a delta H. Remember, we did calorimetry, and we did look in the back of the book and find the table and write down the values, products minus reactants. And we did Hess's law, where you keep or flip. Well, this is the fourth way to find delta H. You take all the bonds of the reactants, add all those up, and you subtract all the bonds of the products. Because when you break the bonds in the beginning, you have to add energy. And when bonds form for products, energy is given off. So the delta H is the difference between those two. Sometimes you might put more energy into breaking all those bonds than you get out. And that means you're adding energy. That would be endothermic. Sometimes you get more energy out from the bonds formed than it took to break them apart. And that would be exothermic. But we're going to take all the bond energy of the reactants minus all the bond energy of the products. Realize that's different than the delta H of formation. And also realize that that equation is not on your sheet. So this is one of those things you're just going to have to memorize and keep in your head. So here's a sample problem. So I have to break the hydrogen bonds. There's the bond energy. I have to break the fluorine bonds. There's the bond energy. And then if we look at what's formed, we have two HF bonds. There's the bond energy. So we're going to take the bond energy of all the reactants up here and subtract all the bond energies of the products down here. And our answer is negative 543.1 kilojoules. So it's just a different way of finding delta H. This is table 8.4 out of your book, and it just shows all the bond energy for different substances. Notice it's different for an N-N bond single than it is for an N-N bond double, than it is for an N-N bond triple. Same thing for oxygen. Oxygen to oxygen with a single bond is one bond energy. Oxygen to oxygen for a double bond is a different energy. You don't have to memorize these, of course. They would be given to you on a test. This model of a molecule is basically saying the electrons don't belong to any one given element. They're shared. So just like if you shared something with your family or shared something with a friend, you might say, well, it's mine and I'm sharing it with you. But if you're truly sharing it, then it really is available for all. So we're not going to say, oh, this electron belongs to oxygen and this electron belongs to hydrogen. We're going to say that this is a region of electrons that both can use. So we're not going to try to keep track of which electron came from whom. In order to do this localized electron model, we're going to, number one, draw Lewis structures. Number two, we're going to predict the geometry. So what shape do they take based on the Lewis structure? And number three, we can talk about what type of orbitals they have. So we're talking about hybridization here. So is it sp hybridized or sp2 hybridized? In Chem 1, you were always taught that every element wants 8 electrons. But that's not always true. We're going to actually expand our ideas about how many electrons everybody can have. Second row elements only can have 8. And that's because they don't have d orbitals. Boron and beryllium can have fewer than 8. Boron can live with 6 and beryllium can live with 4. Everything from the third row down can take advantage of the fact that they have d orbitals to what we call expand the octet. In other words, they can have 10 electrons or 12 electrons. I know it sounds weird, but there are a few instances where that does occur. Sometimes you'll have a molecule that can be written more than one way. This, for example, is a molecule called benzene. Those double bonds don't have to live exactly where they are on the left. They can also move around. So we would say that this thing shows resonance, that those double bonds don't have to live in one certain way. Because remember, the localized electron model says that those electrons are available for anybody. The last thing I need you to do is just get these steps in your notes so that when we sit down in class, we can write Lewis structures. And if you need a little bit more help with that, then you can go back and look at some of the pre-AP podcasts that give you a little bit more detail into doing this. It's been a while since you did it, so I don't think it'll take you very long to get up to speed. See ya.